Now, in this third section that we will now look at is we will now get into the term of molarity. Molarity is an expression that is used for measuring or expressing different solutions. Solutions sometimes work pretty well in many cases, but sometimes in an analytical situation, the difference of percentage for preparing a 33.5 versus 33.7 is very different and very difficult to measure. So for these reasons, we will now learn of a term that is called as molar solutions, and you can, I think by now you know the term M, which is molarity. So excuse me, a molar solution is also represented by a capital M. It's a term that measures the concentrations for many solutions. Now in the lab so far, you have been getting many solutions that have been for example, you did a lab in which we had 6 molar sodium chloride versus 6 molar sodium hydroxide. That was a calorimeter lab, and other labs in which you had 2 molars of a solution or 1 molar. So keeping that in mind, we will now learn of this molar solution, which is capital M equals small m over V. Now I want you to be very clear about understanding this formula. Capital M expresses the molarity of a substance, which is going to be a representation of how many moles of that substance is dissolved in a certain amount of volume. Now keeping this in mind, I can isolate small m, which is this one. You can see the small m needs to be isolated. You would have to multiply both sides of the equation by V, and that's where we're getting capital M over V. Now if you can solve for each one of them, it's going to be very helpful to solve many of these problems. Here we're trying to isolate for V. You can see if we are trying to isolate for V, we must get rid of the small m. I'm doing that on both sides of the equation, but then this gives me 1 over V equals 1 over capital M over small m, and then you can either do the cross multiplication or reverse that equation to get V, small v equals small m over V. Now this is an equation that will come up many times, and if you can isolate for each of these factors, it will be very easy to solve these problems which are with solutions. Now students usually find this quite hard, and I think the reason for that is they're not applying algebra over here. So here we do need to apply algebra to understand or isolate each of these factors. So keeping that in mind, let's look at this word problem, where it says 1 molar sodium chloride solution is prepared by taking 1 mole of sodium chloride, which would be 1 mole of sodium chloride, dissolve that in a liter of a solution. Now these two units are very important to focus. A capital M has to be using small m, which is the moles, divided by liters. So now even if you're given grams in a problem like this, you have to convert 58 grams to a mole of solution, and the total solution has to be in liters. So this is where we'll apply what we learned in the previous chapter, or a chapter or two back, when we learned how to convert moles to grams and grams to moles. So keeping in mind, here is an example that I want to go over with you. Steps for calculation of molarity. There are 4 steps to this process. The first step, for example, let's look at the question first. What is the molarity of 0.5 liter sodium hydroxide solution if it contains 6 grams sodium hydroxide? So here's my classic problem, small m over V. What is this question asking you is to find out what is capital M. So capital M will be determined if we can convert our grams to moles, and we have to make sure that the volume we use is always in liters. So let's check up our problems. Yes, it seems like the volume is given to us in liters. Very good. What about the moles? We don't have the moles. We are given 6 grams of sodium hydroxide. So our step 2, which is our plan plan would be to convert our 6 grams of sodium hydroxide to the X moles of sodium hydroxide. And once you have done that, you can plug into the value. So how do we do that? Is because we learned earlier that the molecular weight of any compound is taking atomic weight of each of its element. So if I take 23 grams for sodium, 16 grams for oxygen, and 1 gram for hydrogen, that totals to 40 grams. So 1 mole of sodium hydroxide equals 40 grams, or 40 grams equals 1 mole. So these are the two conversion factors. We will now begin with our given quantity, which is 6 grams of sodium hydroxide. We will now choose one of the two. Again, notice that we have grams over here, so we are going to put grams on the bottom over here. That converts our grams to moles, and that is 0.15 more. So there are two steps to this problem. The first part is to calculate the moles, and once we have the moles, we'll then go ahead and put the moles on this in this equation of molarity, in which we are saying capital M, small m is 0.15, and the volume is 0.5. You divide it and you come up with 0.3 m, or 0.3 capital M sodium hydroxide. These problems need lots of practice, so do make sure that you practice each of the problems that are in the book, so you have lots of practice with these. Okay. Now let's look at another problem in which we're looking, which is rating as what is the molarity of 325 ml of a solution that contains 46.8 grams of sodium bicarbonate. Again, our problem is capital M equals small m over V. So here is the volume. What is missing over here? The volume has to be in liters. This is showing ml, so this should give you a hint what to do. On the second part of the problem is we have 46.8 grams, but we need to have moles. So here is a problem that is showing that before we go ahead and plug in the values of both, we have to convert both small m and small v for each of the factors. So let's go ahead and see how I've done that in the next slide that's already solved. Here I have taken 46.8 grams of sodium bicarbonate, and this should be over here. It's just a little typo. It should be on the top over here, like 84 grams should have been written over here, but that's okay. How did I come that? Because sodium is again 23, hydrogen is 1, so you add in 23 plus 1 for hydrogen, plus 12 for carbon, plus 16 times 3 because there are 3 oxygen atoms, and it totals to 84 grams. So we have 1 mole of sodium bicarbonate, 84 grams. So my problem is to take 46.8 grams that's given to us, and we can see that we have divided these two factors and we get 0.557 moles. So this is my problem over here. Now the other part was that we had 325 mLs. 325 mLs have to be converted into liters. Same thing. We have 1 liter divided by 1000 mLs. So again, when you divide that, you get 0.325 liters. So now you're going to plug in small m over V to give you your capital M. So we're using the same equation that we learned in the previous section. Another problem that I want to solve over here is using what is the molarity? Again, we're asking what is M. This is what we're trying to find out of a 225 ml of a solution. So that is my V. Again, is it in liters? No, it's not. So this means that this has to be converted to liters of 34.8 grams of potassium nitrate. Again, capital M equals small m over V. You can see that both of these have to be changed. So for part A, I will take 225 ml and I'm going to convert that into liters. And for part B, I have to take 34.8 grams of KNO3 and convert that into moles. So 1 mole equals how many of that. So potassium, you need to go and find out the atomic weight of potassium, find out the one for nitrogen. Again, for oxygen, there are 3 of those, so find out what is the number and times that to 3. Once you have that, I want you to add all these 3 numbers up, and then that would be the value that you will get over here will then be the molecular weight for 1 mole. So you will plug it in here, and then I want you to to add those two up, divide these two values, and you get your answers in mole. So I want you to just to pause over here, solve this, and then we will look at the solved problem on the next slide. So hopefully you did give yourself a little time to review that did you got the problem correct. Here is my answer. 101.1 grams is potassium nitrate. Putting that in, we get these many moles. We set up the moles by the liters, we get 1.53 thing. Now you can, however, once you get the steps in your mind, you can set them all up in one straight line, which is what we're trying to accomplish by dimensional analysis, in which you'd use a one-line statement to convert or to calculate for the given amount of substance. Okay, we